Good afternoon, everyone. Looks like there are many people that suffered the party yesterday. Yeah, I appreciate you made it today. Did anyone win any costume contest? No? Any funny costume that you may want to share with everyone? No? Okay. All right. So if you don't have anything to share, then let's just go to talk about geomechanics. All right. So we're going to start talking about problem number 1. I uploaded a new homework, and this is the first problem we're going to talk about. Let me remind you first, since I just remembered about that we have an exam about 2 weeks from now, okay? So let me get in there. So let's see, this exam is going to be, if I remember correctly, on November the 15th. Okay, here you go. November the 15th, okay? So about 2 weeks from now, we have that exam. And it's going to cover faults and wellbore. So remember, if you have any issue with this and you justify why you cannot be here, just let me know in advance. Okay, so let's talk about problem 691. Problem 691 requires the use of the Kirch's equation in order to tell what are the stresses around a wellbore. And basically, as you see in the problem statement, you have a vertical wellbore with 8 inches diameter, and if it's a vertical wellbore, we're going to look at the cross section of the wellbore, in which, let me just start with square here. The wellbore is going to be here. The diameter is going to be 8 inches. And what else? We have SH mean and SH max. SH mean is acting in direction east-west. So if we add here, this is the north, this is the east. This is going to be SH mean equal to 4,500 psi, and SH max is going into this other direction, perpendicular to that. Remember that always SH max is going to be perpendicular to SH mean, because if this is the principal stress, the other one has to be perpendicular to that. All right, and the other one is going to be 6,000 psi. Okay, what else? You want to calculate here stresses up to 3 feet of distance from the center of the wellbore. And the pore pressure, there's a small typo over there, but the pore pressure in the rock is 3,200 psi, and you're going to consider 2 cases with different wellbore pressure. So the wellbore pressure, that's the one that is going to be applied inside the wellbore. And for all these cases, remember, unless I tell you something different, we're going to consider that we have a perfect mud cake. And that perfect mud cake means that the support of the radial stress is going to be PW minus PP. Okay, so what I want you to do is to calculate what is sigma RR and sigma theta theta for 2 angles, theta equal to 0 and theta equal to 90. Do you remember what we call theta? Theta had a very specific meaning according to where it is measured from. And if you remember, that angle theta is always going to be measured from the direction of the maximum stress, which in this case coincides with the direction of the additional differential stress. So in this particular case, that maximum stress is in this direction, here, and therefore theta is going to be measured from the angle of the direction of SH max. So this is going to be theta equal to 0. So this is the line in which I want you to tell me what is sigma theta theta and sigma RR, and also for theta equal to 90, this is going to be theta equal to 0 degrees, this is going to be theta equal to 90 degrees. And notice that when you have a rotation of the angle, now the theta points in another direction. It's the opposite. Now theta is in direction north-south, and RR is in direction east-west. So along these two lines, from 4 inches to 3 feet, you're going to have to plot what is sigma RR and sigma theta theta. And just to give you a preview of what this is going to look like, let's see, where did I get this from? Here. This is going to look something like this. The plots I want are plots in which this is R, and remember the equations are these are the equations. This is the Kirchhoff equation, and these two are a function of theta and R. Let me add this over here. Sigma RR is a function of R and theta, and sigma theta theta is also a function of R and theta. So when you put all of these equations as a function of R and theta for a given theta and for a given R, you're going to get something like this. Let's say for case number 1 or A, in which the pressure in the wellbore it is equal to 3200 psi. What is going to be the radial stress at 4 inches when R is equal to 4 inches? Which means what is going to be the support in the wall of the wellbore? This is PW and this is PP. Therefore, sigma RR, which is the pressure that you put on the wellbore, if these two are equal, that's the first term of the Kirchhoff equation, that's going to be 0. So there is no support. So this is going to be somewhere over here. And as let's do this one for theta equal to 0 degrees. As you go further away, sigma RR is just going to be SH max minus the pore pressure. So it is going to increase to the far field value of sigma H max. Very, very far away, the rock doesn't feel anything about the wellbore, and the effective stress in this direction is just going to be this one minus the pore pressure, so sigma H max. All right, that's a radial stress. What about the hoop stress at that point? What's going to be the hoop stress at that point? You're going to have to use the Kirsch equation, and I'm not going to tell you right now exactly the value, but that's not going to be 0. It's going to be either a little bit of compression, or it looks like, ideally here, you might have either tension or a compression. I'm not sure. It depends on what are these values. So you combine those values in your equation, and let's assume for now that it is some compression. The value of sigma theta theta, so this is sigma RR, the value of sigma theta theta is going to, let's say it's compression, but I'm not sure about that, okay? It's going to tend to the value very far away. Sigma theta theta is just going to be sigma H min. So it's going to tend to something like this, where this is sigma theta theta and this is sigma RR. When you use the Kirsch equation, you're going to be able to get these two lines and see how they vary with distance. And when you do the same for 90 degrees, theta equal to 90 degrees, for the same pressure, again, sigma RR is going to start at some value over here at the radius, but then it's going to, sigma RR is going to go to sigma H min, and sigma theta theta, now I'm positively sure it's going to be a large positive value. It's going to be a large compression, and it's going to tend to sigma H max. And you have to repeat this also for a pressure in the wellbore equal to 4,000. All right. When you have a pressure in the wellbore which is larger than the pore pressure, and you have a perfect mud cake, what is going to be sigma RR at the wall of the wellbore? It's just going to be the difference between the two, right? So it's going to be 4,000 minus 3,200, 800 psi. And we're going to see that for shear failure, this is good. That's why we use a drilling mat, because it adds support to the rock and makes the rock stronger. So for this one, for again number B, you're going to repeat the same, the plot of stresses as a function of R and as a function of theta. Okay, I am asking you this simplified version of the problem, but you could also plot all the stresses as a function of R and theta for all R thetas, and this looks something like this, like this. So you have the maximum stress, for example, in this case, in direction, let's say in this case, east-west. Your, let me see what I'm plotting here. Oh, sigma RR, in this case, is going to be 0 around the wellbore if I don't have any radial support, but sigma theta theta is going to be the largest here in the north-south in this particular example, because the horizontal stress is coming direction east-west, and you may have tension in these locations. So this is a solution then when you plot that for all R and thetas. All right, so that's problem number 1, okay? It's just making some plots. You do this with Excel, with Python, or with any other software that makes you happy to work with. Let's continue the talk about wellbore stability. And for that, we need to come back to the Kirsch equation. And this is a full Kirsch equation. Let me put it over here. And it predicts, again, stress a function of r and theta for all r and thetas. Okay, but we're not interested in all r's. Right now, I'd like to calculate stresses at the wall of the wellbore, because that's where the stresses are the highest or the lowest. So for these equations, then what I'd like to do is just to get sigma RR and sigma theta theta, and we'll do also sigma R theta for R equal to A, okay? So let me write this in my notes. And probably I'll try to see if I can split this screen in two. All right, so that's a full Kirsch equation. And let's see if I can get this in here. Okay. The first one. For R equal to A and for any given theta. The first term, if R is equal to A, the term in parentheses, the second one is just going to be 1. You see that? And this is just going to be PW minus PP. The second term, if A is equal to R, is going to be 0. And the third term, if A is equal to R, is going to be 0, 2, because it's just going to be 1 minus 4 plus 3, that's going to be 0. So sigma RR, it makes sense that everywhere around the wellbore, it's just going to be PW minus PP, and this is going to be like the radial support. It can be a compression only. You cannot apply a tension here. So if this is a negative value, it doesn't hold. But if it is positive, it's okay. Around the wellbore. And that makes sense, right? It's going to be the same everywhere. Sigma theta theta is not going to be the same. So for R equal to A, then sigma theta theta, the first term is going to be the negative version of the other equation, A is equal to R. Here, now, this is going to be equal to 1. And now this is going to be 2 times this. And let me see. I think, if I remember correctly, there is a simplified version of this. Okay, but we're just going to go with this. So if this one, the term I'm pointing right now here is equal to 2. 2 divided by 2 is 1. So this is just sigma H max plus sigma H min. And the last term is going to be, notice that this term is going to be 3. So 3 plus 1 is going to be 4. 4 divided by 2 is just going to be 2 times sigma H max minus sigma H min times cosine of 2 theta. And sigma theta R is going to be what? One plus 2, 3, minus 3, 0. So if this is 0, everything is going to be 0. And also that makes a lot of sense, because a drilling mud cannot apply a shear on the wall of the wellbore. So that's what is called a free surface, and it cannot have any shear at all. All right, so now with these equations, which are simplified at the wall of the wellbore, we're going to be able to use them in order to tell when the the wellbore is a failure either in tension or in shear. All right, let's go with the first one. The easiest one is tensile. So let me put a complete name. These are called drilling-induced tensile fractures. In a drilling-induced tensile fracture, basically the hoop stress goes to the value of the tensile strength of the rock. And that's going to occur always when, if you look again at, let's go to our first plot over here. The tensile fractures are going to occur whenever theta is equal to 0 or equal to 180 degrees. That means either here or there. And when that's the case, and I fix sigma theta theta to be equal to the value of the tensile strength of the rock that you measure, for example, with the Brazilian test, then we can replace that in this equation, and therefore sigma theta theta is going to be negative Ts. I'm using this equation, and this is going to be the first part. And what is going to be cosine of 2 theta? If theta is equal to 0, then this is going to be 1. And if this is equal to 1, therefore, I just have to add this. And 1 sigma h mean plus 2 times sigma h mean is going to be 3 sigma h mean. And 1 sigma h max minus 2 sigma h max is going to be negative sigma h max. And from here, what I like to do is to find out what is the pressure in the wellbore that is going to cause that tensile fracture. Because this one, I can measure it. I can send rocks to the laboratory and get to know what that value is. Ideally, some of these two also could be known. Actually, we don't know sigma h max very well, but sigma h mean we can get to know that by doing hydraulic fracture tests. So we're going to talk a little bit more about that later on, but let's assume we know that one. Pore pressure, we also sometimes we know that, but what is really the variable design when you are drilling a wellbore is going to be the pressure in the wellbore. So we're going to solve for that pressure in the wellbore. And that pressure, we're going to call it PV, and I'll tell you why it's called PV just in a sec. And if when I move PV is positive over here, it's negative, it's going to go positive on this side. So this is just going to be pore pressure plus 3 times sigma h mean plus sigma h max plus the tensile strength. And it is called PV because this is called breakdown pressure. Whenever you achieve this pressure in the wellbore, that means that the rock is going to fail in tension. And if the wellbore fails in tension and that fracture propagates far away from the wellbore, then you may cause a large hydraulic fracture. That's why it's called a breakdown pressure, because at that point, because of pressurizing the well, you break the well. We're going to see later on that it's not exactly as as this equation says. There is another variable that we have to take into account. But for now, let's just call it breakdown pressure. And remember, this is a tensile fracture, and if it grows too far out from the wellbore, it's going to be a hydraulic fracture. You have a question? Yes. Yes, yes. Minus sigma H max. Okay. Let's try to understand this equation. The breakdown pressure is going to be equal to the pore pressure. That's the first term, and that kind of makes sense, because in order to go above, in order to apply any tangential tension into the wellbore, you need a radial support, and that's why it has to be higher than the pore pressure. Second, so again, this is pore pressure. Second, that breakdown pressure is going to be the lowest when there is a lot of stress anisotropy around the wellbore. That means when sigma H max is significantly higher than sigma H mean, then this difference is going to get smaller. For example, when we were talking about equilibrium of faults, and we said that we could push with sigma H max just a given amount, otherwise the rock would fail, creating faults. Do you remember what that number was? How many sigma H max can I put relative to sigma H mean in a strike slip environment? 3 times, right? So if I'm in condition of strike slip and sigma H max is equal to 3 sigma H mean, that means that this is going to be 0. All these terms are going to be 0. And the only resistance that I have in order to have the wellbore intact or not to fail in tension is just the tensile strength, which is this last term. And it makes a lot of sense that the bigger the tensile strength of the rock, the higher you can put, you can increase the pressure in the wellbore, but the bigger the stress anisotropy, the lowest the value of breakdown pressure is going to be. If, for example, you are in conditions, this is example number 1, and 3 sigma H mean minus 3 sigma H mean is equal to 0. If in example number 2, you are in conditions in which it's isotropic state of stress and sigma H max is equal to sigma H mean, then 3 sigma H mean minus 1 sigma H mean is just going to be equal to 2 sigma H mean. In this case, the near wellbore stresses are adding some compression around the wellbore that are actually helpful in order to increase the breakdown pressure. It's not just the tensile strength of the rock in favor of achieving a higher pressure in the wellbore, it's also the stress anisotropy. But the message here is that the higher the stress anisotropy, the lower the breakdown pressure. We're going to see later on, when we extend the discussion to extended and to horizontal wellbores, that, for example, in strike slip conditions, the least favorable orientation to drill a wellbore is a vertical wellbore, because it's the one in which you have the highest stress anisotropy. Okay, so with this equation, then we're going to be able to compute this breakdown pressure. So let's use this for an example, and that's going to be problem 692. And in problem 692, we have to calculate these values for a given wellbore. And all right, let's see what problem number 2. Okay, so I'm looking at here. Okay, this is a place onshore and 7,000 feet of depth. It's a vertical wellbore. And what else? We have sigma h min, sigma h max, and we have some rock properties right now. Okay, let's see. The first one, it is, we're going to solve pore pressure with hydrostatic pore pressure. So at the location somewhere over here, lambda p is going to be equal to 0.44. And if I make a cross section of this, what this is telling me is that I have sigma h max of 6,300 psi and sh min of where is sh min? 4,300 psi. All right, guys. For double extra points, because I'm rewarding that you made it to this class even after Halloween party. Can you tell me what is PV, breakdown pressure, for these conditions? Okay, so from here you can calculate PP and PV. I'm just going to write the equation again so you don't have to look in your notes. It's going to be PP plus 3 times sigma h min minus sigma h max plus the tensile strength. Yes. SH max is 6,300 psi. Yeah, let me move this a little bit to the left.
Yeah, I got 4320 psi.
4320. And that's a correct answer. Congratulations. What was your pore pressure?
3080.
Okay. And what was, can you make this number, 3 sigma h min minus sigma h max?
Yeah, I can do that real quick.
I'm going to write it in the meantime. What was sigma h min?
1220.
Okay, and sigma h max would be, I have,
3220.
and the tensile strength of the rock is 800 psi. So, okay, I forgot to write this somewhere over here. It's 800 psi. UCS it's this, and the friction angle of the rock is 0.6. Okay, and so this 800, and that's 4320 psi. Very well. So this is the value of PV, and it's going to be very important that we put this into some context of the comparison of these stresses and pressures. Before we do that, where will those tensile fractures occur? Here, in this case, in this first position or in the second one?
The second one.
Very well. Yes, here. So if you were to have any tensile fractures, those would occur there. Okay? All right. So what I was telling you before is that it's going to be very useful, especially when we design a wellbore, that we put these numbers in context. And first of all, let's put in here what is the value of the pore pressure. And the pore pressure was 3080. Okay. So let me see. I want to put all of this in one plot. Okay, so let's say this is 3000 psi, and let's say this is 4000, and here we have 4500 somewhere over there. Okay, the pore pressure is somewhere over here. And what this is telling me, what this equation is telling me, is that I could get the pressure in the wellbore as high as 4320, somewhere around here, and the wellbore will be fine. If I go beyond that value, I'm going to have a tensile fracture. All right. So there's a small thing I forgot over here in this equation. The equation is right, but there is one more component that we have to take into account that we're not going to derive, but here we're just going to add, and it is the thermal stress. What happens when you cool off a rock? It shrinks. But imagine that now you cannot. You try to cool a rock, but you don't let it shrink. Instead of shrinking, what it's going to develop is a tensile stress. So if you hold it and you cool it down, and it's not shrinking, at some point it's going to develop a tensile stress and it's going to break. And with rock around the wellbore, it's the same case, because you have this radial symmetry around the wellbore. If you cool it, it's not going to be able to freely shrink in tangential direction. It will in the radial direction, but in the tangential direction it will not. And when that happens, you're going to develop a thermal stress, which is not going to be good in terms of the breakdown pressure. Many times we drill with drilling mud which has a temperature which is lower than the temperature of the formation. So we're cooling off the rock. And in order to calculate this breakdown pressure, you need to take into account that. And we'll get to this value later on, okay? But just I wanted to mention this in this equation because we'll talk a little bit about that later. All right, so we calculated now what is the pressure that we need in order for this wellbore to develop a tensile fracture. Let's go to shear now. All right, so with the equations that we had before, let me find them. It's going to be this one. Let me get back over here. Okay. All right. We just saw tensile fracture in the wellbore. Now we're going to see how breakouts form. And these are going to be shear fractures. All right. Shear fractures are going to form in locations which are the opposite of where tensile fractures form, and that's going to be when theta is equal to either 90 degrees or 270 degrees. And at these 2 points, what we're going to look at, if let's say this is our wellbore and this is SH max and this one is SH min. This is going to be a point somewhere over here. Okay, at this particular point, we're going to look for conditions in which sigma 1, the maximum effective principal stress, is going to be equal to UCS plus Q times sigma 3, an equation that we already knew, but now we're going to apply it to this context. All right. Tell me, for this point right over here, what is going to be sigma 1? Sigma theta theta or sigma RR? It's going to be sigma theta theta. So sigma 1 is going to be sigma theta theta at R equal to A and theta equal to 90 degrees. And this is going to be UCS plus Q times sigma 3. And sigma 3 is going to be what? Sigma RR. At R equal to A, and it's the same everywhere, so I'm not going to write which theta because it's the same. So that's it. The only thing we have to do now is to put what is sigma theta theta at these 2 parameters and what is sigma RR. But the important thing to notice over here is that sigma RR is acting as your minimum effective principal stress and is adding support to the rock. Remember that the higher sigma 3, the stronger the rock gets. It's the same rock. And this is going to play a fundamental factor here because the higher the support, the wellbore support that you have on the wellbore, the stronger the wellbore is going to be too in terms of shear. All right, so let's do this. For theta equal to 90, sigma theta theta, you can see the equation here on top, but basically this one is going to be 180, and cosine of 180 is going to be -1. So all of this is going to be PW minus PP plus, if this is negative, now this is going to be positive, plus 2 sigma H max. So it's going to be 3 sigma H max minus sigma H min. That's going to be sigma theta theta, and that's going to be equal to UCS plus Q, and sigma RR is just going to be PW minus PP. You can play a little bit more with these equations and finally get to the final equation. But again, what we want to do here now is, assuming that we know sigma H max, sigma H min, that we know UCS, we know Q, we want to solve for PW, which is our design parameter. That's what we can vary with the wellbore mud density. And we're going to call that PW as PW for failure in shear. And after you play a little bit with those variables, you will find that this is the final equation. And what this is telling you is that the pressure in the wellbore at which you're going to have shear depends on the pore pressure, again, depends on stress anisotropy, which again appears in this equation, and depends on the strength of the rock. The stronger the rock, the lower this value of PW shear is going to be. So here, PW shear is going to act as a pressure that is going to be what is called a lower bound. What is the lowest pressure that you can get in the wellbore so that the rock doesn't fail? If you have a high support, a high sigma RR, the rock is not going to break. But if you start lowering sigma RR, or you start lowering the pressure in the wellbore, at some point the rock is going to start to break. And if you lower it more, it's going to break even more. So we can also find an equation whenever we have failure around the wellbore, but instead of having a very tiny failure at the wall of the wellbore, we let that failure to progress a little bit more, to create some shear fractures, and to grow to some size, same in this direction. And that's going to be achieved by even lowering the pressure below this value. So when you get to grow this failure more, you're going to see that there is quite a bit of shear failure, and this is going to be called breakout angle. If the equation that we just developed is the one for when the breakout angle is about 0 degrees. So it's a very tiny failure. But sometimes we can let shear failure happen in a wellbore with a breakout which can be at about 40 degrees, 50 degrees, something stable, and the wellbore is still going to be fine. And that's going to be another design parameter. So we can extend this equation. Instead of doing the equilibrium just at the point as we did before, right here in the middle, we can do the same equilibrium equation here, and we can write this equation as an extended version of the previous one, and it's going to be equal to the pore pressure equal to what we had before, plus, let me continue in the second line, sigma H max plus sigma H min now this is going to be a function of the breakout angle, sigma H min remember, all of these equations are in my notes too, okay? And now this equation is going to be good for a breakout angle which is more or less smaller than 70 degrees. You may use it for 80, sometimes a little bit more, but to be conservative, for less than 70 degrees, this is going to be fine. So now we have an equation that tells us what is going to be, either if we have a breakout angle design, let's say 45 degrees, what is the pressure in the wellbore I need in order to cause that? Or if you have some given pressure, what is the wellbore breakout that is going to form? And the second part of the homework over here is just to calculate those two quantities and also with a given breakout angle to tell what is PWBO. We'll continue talking about this on Monday, and I made also the homework available, and it's due on Tuesday. All right? It's not too difficult. Don't worry. Have a good weekend, guys.